Welcome back. This is our second video in our unit. We're going to discuss using dimensional analysis, which was the topic of the first video, along with molar mass to actually do some dimensional analysis with some chemistry kind of topics going on here. So you'll want to grab a calculator so you can try out these calculations as we go. The topic is, as you can see, molar mass, and we'll get into what that means and how that works in just a moment. So I want to point out that we did last time dimensional analysis railroad tracks, and we used it to convert between money units and inches and feet and things like that. Well, we're going to apply it to something that is definitely a big deal in chemistry, and that is how we package our atoms. Okay, so we're going to be looking at how we package our atoms, and I say that because I want to draw a similarity to things like a dozen. If I say a dozen, you automatically think 12. If I say a ream of paper, you automatically think 500 sheets. Well, we have such a thing in chemistry. This thing in chemistry is what we use for atoms, compounds, molecules. And I'll get to what amount it is, but I want to let you know this thing is called the mole. M-O-L-E. We're not exactly sure in chemistry where this word comes from. There is discussion that there is a Greek word for pile. That sounds very similar to it. I don't speak Greek, so I don't know. There's discussion maybe it was supposed to be an abbreviation for something, and no one bothered to ask the guy who started it like what it was an abbreviation for. But we call it the mole. That's just the name of it. And so like a dozen, if I say dozen, you're like, oh, that equals 12 of something. Well, if I say mole, I want you to think, oh, that equals this of something. Okay, this is the number that it equals. 602 sextillion, 200 cotillion of anything. Okay, so I could have certainly a mole of roses, although with this number as big as it is, I doubt there's ever been enough roses in bloom in the existence of the earth for there to even be a mole of roses. If you imagine having a pile of baseballs with that many, you're talking something the size of the moon. And then yet, atoms and molecules and compounds are so small that a mole of water is about 18 milliliters. Now keep in mind, a bottle of water, your normal bottle of water that you get, that's about 500 milliliters. So imagine just to be 18 milliliters in the bottom of that bottle. That would be that many molecules of water. So molecules and compounds and atoms are that small. We need that big a amount of them to be able to really easily work with them and measure them and move them around and things like that. Be aware this is often called Avogadro's number. Mr. Avogadro came up with the basic mathematical premises that allows us to calculate this number. And we do usually abbreviate it in scientific notation because no one likes writing 21 zeros after that too there. Now, a former student sent me this picture from a product he saw in a store. It's called Avocado's number guacamole. So not Avogadro's number, it's Avocado's numbers guacamole. And there's Avogadro saying let's party arriba. And so notice their claim. They have in their package of guacamole, they have over 5 avocados, which clearly is the same as that. Well, no, it's clearly not the same as that big number. But that's what they claim. And they do admit it right here that there aren't that many avocados in there, but they say 5 plus avos isn't bad. Okay, I'm not going to buy a product that reminds me of this number, yet only has 5. But I did find it interesting that someone was like, oh, Avogadro's number, let's make it Avocadro's number or something. Okay, so just a little side note, something I saw, something going on in the store. We're going to use the mole to tell us for atoms and compounds, how much to measure out. So if we're measuring out amounts of elements or compounds, we're measuring out grams. How many grams am I going to measure out on my electronic balance to have a mole or 2 moles or however many moles I'm wanting? In order to do that, I'm going to be using molar masses. And as the name implies, we have mole and we have mass, which is grams. So this is actually a conversion factor. Just like we looked at last video, we need that conversion factor to get from one unit to another. I can get from moles to grams and grams to moles with a conversion factor of what we call molar mass. Okay, so here's good news. Like, you don't have to figure out molar masses. Scientists have already done it for us and put it in a very nice, neat, organized table called the periodic table. So I took a box for sulfur from the periodic table, and that number on the bottom there, the one that will always be a decimal, that's your molar mass. That is the grams for 1 mole of that element. So if I tell you in lab, hey, measure out 1 mole of sulfur, you're going to measure out 32.07 grams, because that's our balances only go to the hundredths place, so that's what you'd have to round that to. But what if I said 2 moles? Well, if that's for 1 mole, then I just multiply it by 2 and I get 2 moles worth. And what if I wanted 3.5? I would multiply by 3.5. And what if I wanted 2/3? I'd multiply by 2/3. So you do see how convenient this is? This is the grams. That is equal to 1 mole of that element. It's a conversion factor. 1 mole of that element is equal to that many grams. That many grams is equal to 1 mole of the element. So with it being a conversion factor, I can put it into my railroad tracks, the ones we practiced just by themselves last time. So let's give this a try. Student measures out 12 grams of magnesium. How many moles did that student measure out? So like as the student scooping it into a little cup, how many moles of magnesium is going to be in that cup? Well, I start my dimensional analysis the way I do any dimensional analysis, and I put the given in the top left box. That's just what I do. So that number went there. And I like to add the label of the element I'm working with there. Sorry, I just noticed I made it go unfocused. Okay. I like to add the label there. You don't have to. You absolutely need that label, grams. This is 12 grams, and you could write out grams, okay. Whether or not you include the elements label, that's not necessarily something that has to be there. You can go without that. Okay, so I put my 12 grams there, and now I know to match diagonally. So down here, I'm going to put another grams, so that my grams and my grams match diagonally. How many grams I need a conversion factor. So what you need to do is you need to go to a periodic table and you look up the box for magnesium and you need to see what number it tells you in the box for magnesium. Again, that's the grams in a mole. So how many grams? 24.305 grams. That's from the box for magnesium. It'll be like magnesium, it'll be 12, it'll be 24.305. That's a 3 at the bottom. Okay, that's where that comes from. And again, that is for 1 mole. It will always be 1 mole. You won't have a number other than a 1 there. Anytime you use the periodic table, it's got to be for 1 mole. That's how the periodic table was designed. That's what it's got to be. Okay, so grams I matched with grams. I knew what number went with grams because that's the number for the grams on the periodic table. And I put 1 mole because anytime I use the periodic table, it's 1 mole. Okay. Now grams cancels grams, and I do the math and give it a try. Pull out your calculator, give it a try, see that you get what I got. I wanted to round to the thousandths place, so I did. And that's how many moles, and moles is abbreviated M-O-L. I don't know why we take a word that's only 4 letters and we abbreviate it to 3. But that's our abbreviation. And if we have more than 1 mole, we just add an S to the abbreviation to moles. It is what it is. I don't know why we abbreviate such a short word already, but we do. Okay, so that was if I knew grams and I wanted moles. Now I know in my little cup that I measured out that had 12 grams of magnesium, it's got almost half a mole in there. It's got 0.494 moles of magnesium. What if I know the moles and I want the grams? So like you're in a lab and all I tell you is I need 2.3 moles of boron before we can get started on with the reaction. How much are you going to measure out? Well, we start our rototrack the way we always do with our given information and my label of moles. And again, I put the boron. That's just a me thing. You don't have to put the boron there. And now I'm going to match that label diagonally. Okay, so I'm going to put the moles there, and it's always 1 mole. What do I get for a mole of boron from the periodic table? Well, you look it up and you get 10.812 grams. Okay, so moles is going to cancel moles. And I can see the math is going to be multiplication. So give it a try on the calculator and see if you don't get that. 24.868 grams of boron. So in lab, I want to take my little like cup or whatever thing I'm measuring into, and I want to measure in 24.861 grams. And then I know I have that 2.30 moles in that cup. Okay. Well, that works for elements. What if we have compounds? Well, the good news is it works out pretty well for compounds too, but there's just an added step to it all. Before I can do a rototrack, I need to find the molar mass for the compound. And we don't have compounds up on a big chart that you can just look up their molar masses. So I want to point this out. If I know a formula like sodium carbonate here is Na2CO3, that ratio tells me for one compound I have 2 atoms of sodium, 1 atom of carbon, 3 atoms of oxygen. That ratio also tells me if I have a mole of the compound, I have 2 moles of sodium, 1 mole of carbon, 3 moles of oxygen. So knowing that those ratios work for the mole as well means I can find the mass for the entire compound. So we call that the molar mass of the compound, or sometimes the formula mass, because I'm using the formula, and the formula is Na2CO3. I'm using that to find the molar mass. Okay, so let's do that. Let's find the molar mass for sodium carbonate. So again, ratio time. So how many, I don't know why it loses focus when I get in front of it. Okay, so how many sodiums? I have 2 sodiums. How many carbons? 1 carbon. How many oxygens? 3 oxygens. So I'm literally going to take 2 times the number for sodium from the periodic table. I'm going to take 1 times the number for carbon from the periodic table, and that's grams per mole, because again, conversion factor, it's however many grams equals 1 mole. We just don't write the ones. Okay. And I'm going to take 3 times the number for oxygen from the periodic table. So I do the multiplication, and I get these subtotals, and then again I want like one number for the whole thing. If I want a number for the whole thing, I've got to add them up. So I'm going to add up my subtotals, and then that's my molar mass for sodium carbonate. Of course, you can pause it if you need to keep writing. But what do I do with this? Well, the answer is I use it in my rototracks. How do I use it in my rototracks? Well, either this way or this way. So how do I know which way to use it? I can't tell you because I don't know. You let the railroad track tell you. If in the railroad track you need to match moles diagonally, then you would use it this way. If in the railroad track you need to match grams diagonally, then you would use it this way. So it's a conversion factor. 1 mole of sodium carbonate is that many grams. It's a new conversion factor. We can use it in our rototracks, but which way it goes in the rototrack depends on the railroad track. Let the railroad track guide you. Step 2 is just to match diagonally your labels. If you can do that, then it'll tell you which one of these is appropriate for the situation. So let's do another example of molar mass for a compound because I want you to see this. Here I have calcium nitrate, and I picked this because this has parentheses. So I want to like remind you how this works. I still have 1 calcium, so it's 1 times the mass for calcium. But that 2 outside the parenthesis goes to the nitrogen. So I have 2 times the mass of nitrogen. And the 2 also goes to the oxygen, which I already have 3. So 2 times 3 is a total of, see that, 6. 6 oxygens. So when you have a compound with parentheses, the number outside the parentheses gets distributed to everything inside. Students often ask me about something like OH with a number outside. Yes, it goes to the O, and yes, it goes to the H. It goes to everything. Like, I don't know what else to say other than everything in the parentheses gets multiplied by the number outside. And they're like, well, what if I have something like xenon out here? Well, no, because that's not in the parentheses, so it's by itself. Okay. Anyway, so I just wanted to point out how the parentheses works, remind you how that works. And again, I do the same thing. I just multiply through, I find a grand total, and there we go. Okay. So we're going to do a few more examples, but before I do these few more examples, the examples are going to use potassium oxide. So I'm going to need to find first the molar mass of potassium oxide so I can use that as a conversion factor in my rototracks for potassium oxide. So I have potassium oxide. What does that really mean? Well, that means I have 2 potassiums and 1 oxygen from my formula. What does that tell us? 2 times the mass of potassium and 1 times the mass of oxygen. What that means is I could just type that into my calculator if I'm very careful and hit equals, and I get the molar mass for the compound. So what I want you aware of is you have the freedom not to have to do this every time you need a molar mass. I give you that freedom. If you feel confident that you can do it all one line in the calculator and get the correct answer from the calculator, go for it. You have that freedom. If you are like me and you battle dyslexia or whatever else might distract you from your work, then often it really is helpful to write some stuff down to help you stay focused and be sure no numbers go flipping in your head, because the numbers flip in my head so easily. It can get scary. So if you need to write them down, you have the freedom to write them down. You're welcome to always use the margins of papers to write them down, and I'm totally okay with that. If you can do it totally in your calculator and not mess it up and do it all at once and not need to write down a single thing, you have the freedom to do that. I give you that freedom. Okay, so pick which way you need to go on that. But notice I have a conversion factor. 1 mole of potassium oxide is worth that many grams. So 9.195 grams per mole, per 1 mole. Okay, let's use that now. So 2 final examples. I'm going to have 560 grams of potassium oxide. Maybe like in the lab tomorrow, you've scooped out 560 grams of potassium oxide and you've put in a little cup. How many moles did you just put into the cup? Well, we start our rototrack the same as always with our given information. And this is where I let the rototrack guide me. Check it out. I have grams there, so I know I must end up with the grams there. How many grams? Well, we just found out 94.195 grams. And where I put that grams on the other side is always 1 mole, because that's what the periodic table works for. 1 mole. 1 mole. Always 1 mole. Never more, never less. 1 mole for the periodic table. So this molar mass is grams per 1 mole. And I put that in there and I do the math. I'm going to divide. So I'm going to divide in the calculator. Give it a try. Pull out your calculator. Do it, do it, do it, do it. You know you want to do it. Do it. Okay, and give it a try. And we get that many moles potassium oxide is in my cup. If I measure out that many grams, I'm holding that many moles in my cup, which kind of gives some legitimacy to the idea that mole might mean pile. If I have that many grams, how big's my pile? 5.945 moles worth. Okay. What if I tell you in lab I want a certain amount of moles and the challenge is for you to measure out the amount that I need? Well, how would we do that? Well, we would start our rototrack with the given information and we would match the label diagonally. So I see the word moles here, it needs to match diagonally here. So this is where I put the 1 mole, and then up here is where I put the grams that we calculated. So it's always like one place or the other if you haven't figured out. It goes here or here, but both pieces are there. They might be flipped, they might not be. How do I know? I don't know. Let the railroad track guide you. They must match diagonally. Have I said diagonally enough times that you believe me that the labels must match diagonally? Moles as labels cancel out, leaving me, when I do the math, with grams to put here on the answer. So there's my grams right there. And that's how many grams you would be measuring into the cup to get 3.4 moles into the cup. Okay, that's the only new addition to our dimensional analysis we started last time that I want to get to. That's it for right now. We're going to do some practice with this, and then we'll come back and we'll add a little more later and a little more later, and we'll just keep going with it until we get all these great chemistry concepts that dimensional analysis works for figured out. But that's the idea of molar mass. The periodic table tells us the grams, the mass for 1 mole of any element. And if I have a compound made up of many elements, I just add it all up from the periodic table, and that's how many grams per mole. And I can use that as a conversion factor in my dimensional analysis. That's it. I hope this has sunk in. Be sure you focus on the practice to make sure that it sits in and gets stored in your brain. And good luck.